Okay, so today we are doing section P3 on radicals and rational exponents, which are kind of the same thing because rational exponents you turn into radicals. All right, so to start with, we need to make sure we understand the definition of the principal square root. You can read that, it's very convoluted. Basically, what we mean by the principal square root is that we are only going to have positive answers. When you take the square root of something in the middle of working, like solving an equation, we always tell you to put plus or minus. But if you're just simplifying an expression, we assume principal values, which means we assume the positive answer. And then remember that square root means that you are wanting to take something out for anything that there's two of, like the square root of 9 is equal to 3 because this was 3 squared. So the square and the square root undo each other is really the general idea. So that's all those two blue boxes really mean, is that we only want the positive, and square roots are just what number multiplied by itself gave you that number, but it's not always quite that simple. So we have the product rule that says that if we have two square roots being multiplied, you just multiply the square root of the product of those. And the same thing works with the quotient rule. We can just divide them or we can separate them. So both of these properties work both ways. Sometimes we need to separate and sometimes we need to combine to be able to simplify. All right, so some examples using those ideas. If I just want to evaluate or simplify, I'm going to figure out what does it equal. So here we have the negative square root of 9. So the square root of 9 is 30, and that negative just means negative 30. Now I know I just said your answers need to be positive. My point on that was that the square root of 9 is going to be positive 30, but that negative on the outside can change it back to a negative. All right, number 2, we can't divide 1 over 25, but if we use the idea that I can take the square root of the top and then take the square root of the bottom, then we can simplify because the square root of 1 is 1 and the square root of 25 is 5. All right, so here, the square root acts like grouping symbols. So order of operations says I'm going to have to add first. So this is what the square root of 25. And the square root of 25 is 5. All right, number 4, this, you're going to have to take the square root first and then add. So the square root of 9 is 3. The square root of 16 is 4. 3 plus 4 is 7. All right, number 5, the square root of negative 49. Now in Algebra 2, probably in Algebra 1, you talked about what happens when you take the square root of a negative and you get an I and all of that. Well, we're not there yet in this class. So at this point, you're going to stop and tell me that it's a non-real answer and be done. The square root of a negative, at this point, we're not going to handle. It's just non-real. I just need you to understand that it's not a real answer. All right, so number 6, on the other hand, you see how it's in parentheses? It's negative 5 squared. So if I told you to take the square root of that, remember square and square root undo each other because they're inverses, it would just be 5. Well, the fact that there's parentheses around this negative 5 means that that square and that square root can undo each other, and it's just equal to negative 5. All right. So those are the simple, straightforward. What happens when I'm not giving you perfect squares to deal with? All right, so in that case, it's important that you know what numbers are perfect squares. So in this little box right here, I'm going to apparently make the whole screen jump. Hold on. All right, I'm going to make a little box, and we're going to write our perfect squares. All right, so we have a perfect square of 1. Its square root is 1. So we know 1 squared is 1. We know 2 squared is 4. So perfect squares is this column. We know 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. We should be able to go farther than that. You can go 11, 12, 13, 14, 15. And then you should also know 20. All right, I'm kind of running out of room to make my list. So I'm going to stop there. But I want you to go ahead and finish it out. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. 15 squared is 225. And then 20 squared is 400. Those are the ones that I need you to be able to recognize and make your life a little easier. There's 2 ways to think about simplifying a radical. If you know these numbers, it's easier to do the shorter way. So we think about the number 48. We want to know which one of these perfect squares will divide evenly into 48. And I believe the answer is 16. 16 times 3 is 48. So we have that property that says we can take the square root separately. So the square root of 16 is 4, and the square root of 3 is ugly, and it is simplified. All right, number 8. We can't simplify either one of those because 5 is prime, and 10 only has factors of 5 and 2. So we're going to multiply it together and get 50x squared. All right, so then we're going to try to break it into pieces where I have a perfect square. So out of your list of perfect squares, which number goes into 50? And you want to choose the biggest if there's more than one. Like on 48, I could have chose 4, but there's something bigger, so we went with the 16. All right, so for 50, I believe 25 and 2 is going to work. And don't forget that x squared is there. And again, take the square root of the pieces individually. The square root of 25 is 5. The square root of x squared is x. And the square root of 2 is ugly, so he stays in the house. All right, so number 9 is as simple as take the square root of the top, take the square root of the bottom. And the reason that I know that is because both of these numbers are on my list of perfect squares. So if I just take the square root of 25 and the square root of 16, I'm done. All right, number 10, it looks to me like I can just divide that. So just like I can separate it to simplify, I can put it back as one big radical. So I think about this as one big radical. I can do the top divided by the bottom. So 150 divided by 2 is 75. And x to the third divided by x is x squared. Using the property that we learned in the last section, we can do 3 minus that understood 1 and get 2. But that's still under a radical because I haven't taken the square root of anything. I just divided those numbers to make them smaller. All right, so now we're looking at 75. How do I simplify that? Well, which one of your perfect squares goes into 75? If there's more than one, then go with the bigger. So 75 is 25 times 3. Don't forget the variable piece. So we're going to take the square root of each piece individually. The square root of 25 is 5. The square root of x squared is x. And the square root of 3 is ugly. He stays in the house. All right. When we're adding and subtracting radicals, they have to match. It's just like fractions or anything else where you have to have like parts, like combining like terms. So in order to put 2 radicals together with addition or subtraction, they have to match. Well, these don't match. But if I simplify them, I can probably make them match. So if we think about 27. So first of all, this has 5 times 27. There's understood multiplication there, so this is going to be 5 times. Split 27 up into 9 times 30. Take the square root of what you can. So again, this is 5 times. The square root of 9 is 3. The square root of 3 is yuck, so it stays. And so now I can just do 5 times 3 and have 15 root 3 as a simpler version of 5 root 27. All right, so we'll have a big plus sign. And we're going to clean up the 12. Now the idea is to make them match. So we know we want to use 3 times something. And 3 times 4 is 12. So for 12, we're going to split it up into 3 times 4. And I know I wrote 4 times 30. It's okay. That's the commutative property at work. All right, so the square root of 4 is 2. And the square root of 3 is, yep. So it stays. So now we do have like pieces. We have root 3 on both. So if I have 15 root 3's and 2 root 3's, that's 17 root 3's all together. All right, number 12, same concept. Try to simplify what you can to make some pieces match. All right, so this guy, we can't do anything with because he's not squared and this guy's prime. So the square root of 7x is going to stay. All right, for 98, we've got to think about which one of our perfect squares we think goes into 98. And I'm thinking it ends in 8, so maybe 49. Is 49 times 2 98? Yes, it is. So we can do this as 49 times 2. So I'm going to try to kind of skip a step, so make sure you're listening. If I do this as 49 times 2, that's 7. That's going to stay, and that's going to stay because he's not squared. So outside is a 7, but underneath will be a 2x. All right, now this guy's also just going to come down like he looks because 2 is prime and x is not squared. All right, so now we got to work on this last one. 28, hopefully, we know is 4 times 7. So again, if you take the square root separately, this is a 2. This stays the square root of 7. Remember that this 5 is out here for it to multiply by. So that'll be 10 square root 7. And don't forget this x was there. All right, so now we're looking for like pieces. So we have the square root of 7x here and here. So here there's an understood one of them, minus 10. So 1 minus 10 is negative 9 of those square root 7x's. And then we have these guys that both have the square root of 2x. So I can do 7 minus 1 gives me 6 of those. And I'm done because I don't have any more like pieces. Okay, so let's see. I think that's it on this one. Yes. All right, so now we're going to talk about rationalizing the denominator. So if the denominator has a radical in it, there's a rule in math that says you can't have that. So if it's just a single radical, it's as simple as multiply the top and the bottom by that radical. And what always happens in that case is the radical moves to the top. You get something like this where you have a square root of a square. So it falls off the bottom. So you can always jump straight from here to here without doing any work. And I'm okay if you remember that that trick is there for you to just jump to that. If you need to show the work, that's fine. If we have more than one piece in the denominator or 2 radicals in the denominator with add or subtract, then you have to multiply by what's called the conjugate. And all the conjugate is you change the sign. So we keep the front and the back. We just change whatever that sign is. So if this was a plus, we'd make it a minus here. And you multiply the top and the bottom by that. And it's a matter of distribute. So you do this times this, and you do this times this. All right, so what's happening here is when you multiply conjugates, you're always going to end up canceling out the middle terms. So you really only have to do the front times the front and the back times the back, which is going to get rid of your square root. So let's look at an example with numbers in it because those are always easier. All right, so number 13, if we're going to rationalize the denominator here, we can multiply the top and the bottom by the radical in the bottom. Now, if you see that you can simplify your radical, sometimes that saves you work down the road. So I think that I'm going to do that here before I do this step. All right, so I know that 12 is 4 times 3, using what we did a while ago. We can call that 2 root 3. So I can say that this is the same thing as 6 over 2 square root 30. Well, then you can notice that you have 6 divided by 2. So you divide that 2 into the 6, you got a 3 on top and the square root of 3 on bottom. All right, so now comes the rationalizing part. If I take this 3 over the square root of 3, to rationalize, I multiply the numerator and the denominator by that radical that was in the denominator. So on top, when I multiply a regular number by a radical, they just literally sit beside each other. On the bottom, you get the square root of 9, because 3 times 3 is 9, which is 3. And usually you can stop here, but you see this one, you actually have these 3's that will divide. So if you divide those off, then we end up with just root 3 as the final answer. All right, so again, this last step is not always going to happen. You're not always going to be able to clean that up. All right, so since you're not here to ask questions, I'm going to go ahead and do one more of those. So let's say that I give you something like 7 over the square root of 5. All right, for this one, to rationalize, you're just going to times root 5 on top and bottom, which is going to give us 7 root 5 on top, the square root of 25, which is just 5 on bottom, and you're done because there's nothing there that'll simplify. All right, so if I give you one where there's more than one piece in the denominator, so usually they're going to look like this instead of having radicals in both places. All right, so to rationalize, you multiply the top and the bottom by the conjugate of the bottom. And remember, conjugate is the exact same thing, just change the sign in the middle. All right, so on the numerator, we're going to do 7 times 5 and 7 times negative root 3. On the denominator, I'm not going to write every piece down because some of them are going to cancel out, so listen carefully. We're going to do 5 times 5. You're going to do 5 times negative root 3. Then you're going to turn around and do 5, all right, like this. You get 5 times negative root 3. And then you do 5 times root 3. And you see how that's the exact opposite of each other? Those would make 0. So I don't ever write those down. I know that when I multiply conjugates, those middle pieces are always going to cancel out. So when I'm rationalizing my denominator, I always just do the front times the front, and then the back times the back. So that's going to give me negative square root of 9, which is just 3. All right, so now up top, there's nothing that I can do because he doesn't have a square root and he does, so leave him alone. But on the denominator, I should be able to get a single number, and I believe that's going to be 22. All right, now keep in mind that if you get to this point and you see that all of these regular number pieces will simplify by the same thing, you can do that. All right, so again, since you're not here, let's do one more of those together. See if I can make my color change. All right, so let's say that I give you, I don't know, 2 over the square root of 7 minus 3. All right, so to rationalize, you're going to multiply the numerator and denominator by the conjugate of that denominator. All right, so our numerator, we're going to do 2 times both of these pieces. So we'll have 2 square root 7 plus 6. For the denominator, we know how conjugates work, so we can just do root 7 times root 7, which is the square root of 49, which is 7, and negative 3 times 3, which is negative 9. All right, let's see if I can slide down. Okay, so again, numerator is not usually going to simplify at this point. The denominator, you can put those together and have negative 2. All right, this one, randomly, I made it up off the top of my head and it worked out like what I was talking about. If you look at all of these numbers, this number, and this number are all divisible by 2. So if you'll divide all of them by 2, this is a 1, so you have 1 root 7. You don't have to put the 1 in front of the square root of 7. You divide this by 2, you get 3. Since the bottom was negative, I'm going to go ahead and divide these both by negative 2. So this would be negative 1 root 7. This would be negative 3. And when you divide negative 2 by negative 2, you get 1. So this is like over 1, or leave it be. All right, so next we have the principal nth root. So we've been talking about square roots up to this point. Now we're going to move on to taking other roots. So nth root just means any number can go there. So if I'm taking a cube root, it'll look like this. Or I could take a fourth root. It'll look like that. All right, what you need to keep in mind when you're doing these is that sometimes you can get non-real answers. So just like taking the square root of a negative is non-real, anytime you take an even root of a negative, it's non-real. So if this little number here is even and the thing underneath is negative, then that's automatically non-real. But if it's odd and the thing underneath is negative, then you would just get a negative answer. Okay? All right, so if I'm taking a cube root, that means I need 3 of something to be able to pull one out. So the way a square root works, if we back up for just a second, if I'm telling you to take the square root of 50, we break it down to 25 times 2, right? So if we break it down 25 times 2 and then break the 25 down to 5 times 5, and we're talking about its prime factorization, which looks like this, then because there are 2 of these, one of them comes outside. Because the 2 is lonely, he stays inside. Okay, that's another way to think about the square roots, and that may be easier for you when you're dealing with the cube roots and fourth roots, because those aren't ones you're going to have memorized off the top of your head usually. It's a good idea to have some of them memorized, and we're going to work with a lot of them over and over and over again, so you'll pick up on them. So some that you should probably know. The cube root of 8 is 2, because 2 times 2 times 2 is 8. The cube root of 27 is 3, because 3 times 3 times 3 is 27. All right, those are some cube roots that you should probably know. Beyond that, it's really not like crucial that you memorize anything. You're just gonna play with the numbers and see what happens. All right, so I'm gonna do the cube root of 40. We break 40 down. The first thing that comes to mind, 4 times 10. All right, so then 4 breaks down to 2 times 2. 10 breaks down to 5 times 2. So we rewrite this cube root of 40 as the cube root of, and say 2 times 2 times 2 times 5. There are 3 2's. So that means 2 comes out. There's only one 5, he stays in. Here's my simplified form. All right, so next we have the 5th root of 8 times the 5th root of 8. Okay, so first of all, I'm going to go ahead and combine these and call it the 5th root of 64. All right, so then what do we know about 64? Well, we know it's 8 times 8, right, because we just did that. We know this is 4 times 2, and this is 4 times 2. And these 4's are both 2 times 2. All right, so we write down the prime factorization instead of 64. That's 1, 2, 3, 4, 5, 6 2's. All right, so it's a 5th root. So for 5 of them, 1 comes out. And then that one lonely guy is left inside. All right, because this right here would be 2 to the 5th, and a 5th root cancels out to the 5th. Okay, so same thing if we're adding or subtracting, the radical parts have to match, just like with the square roots. So I want to try to make these match. I know this is prime, I can't clean that up. So I'm thinking 81 can break down into 3 times something. I think it's 27 times 3. All right, and then I just told you that one of the cube roots that you should probably know is that the cube root of 27 is 3. So we're going to have the 3 from outside. We're going to have the cube root of 27 is just 3. And then we have the cube root of 3. Holy mess, that's a lot of 3's. So that becomes 9 cube root of 3. Bring this guy down, minus 4 cube root of 3. So that's 9 minus 4, 5. So you have 5 cube root of 3 as your answer. Okay, I'm pretty sure this is the last thing, rational exponents. So first of all, I need you to understand that this property exists. Nothing else up there do you really need to understand, just the fact that that property exists. So do you see how this is the root and this numerator is the exponent? So I can take a fraction exponent and write it as a radical, or vice versa, to be able to help myself out. Usually it's better to take the fraction exponent and write it as a radical. All right, so if I want to work this problem, then I have to understand that this is the 4th root of 256 to the 1st. All right, so then the 4th root of 256. Okay, so first of all, I recognize 256 as maybe having a 4th root. It makes me think that it does. Like, it's just in my head that I think it does. That's not something I expect you to know, but you can always stop and check. So if you have the graphing calculator, if you click the math button, which is the 3rd button down, then cube root is there, and then underneath that there's one that has X in that little radical. So if you choose that one, it will allow you to type in the 4th root and then put 256. So if you don't have a graphing calculator at home, your cell phone calculator, if you turn your phone sideways, will do a lot of the things that you need it to do. But you also, on your cell phone, can download an app called Calc84 or Calculate84, depends on which kind of phone you have. And it's almost identical to the TI-84 that I have in class. And so it'll have like the same basic button. So it should have a button that says math. When you click it, it should give you an option to put in a 4th root. So if you do a 4th root of 256, the answer is 4. All right, so number 19. If we change this to the cube root of 27 to the 4th, and that's using this guy right here, then we can do the cube root of 27, which is 3, and do that to the 4th. And 3 to the 4th is 81. And again, you can do that in your calculator if you don't know that 3 to the 4th is 81. You can honestly just type this in on the calculator exactly like it looks and get an answer, but the idea is that you understand how the properties work, which is why I'm showing you the steps. All right, so here, this looks like those problems that we worked with the exponent properties in the previous lesson, and that's exactly what it is, because you can add fractions just like you can add regular numbers. So here, this is a multiplication problem, so you're going to multiply 2 and 5 because they're regular numbers, but you're going to add the exponents of those x's. All right, they were nice to you. It's 4 thirds plus 8 thirds, which is 12 thirds, which is really just 4, and you're done. All right, the next one, you're going to divide the regular numbers because it's a fraction and division problem. So 20 divided by 5 is 4. You're going to subtract the exponents because it's dividing, and that's the exponent rule when you divide like bases, is subtract those exponents. All right, so you're going to have 4x, and you got to figure out what is this exponent. Well, if we come over here and we think about what this is saying, remember this is over 1, I need it to be over 2. So it becomes 8 over 2. 1 times 2 is 2, 4 times 2 is 8. So 8 minus 3 is 5. And you write this as 5 halves. And honestly, you're done, because if you change it to the square root of x to the 5th, you're not really helping yourself a whole lot. You could kind of simplify if you write it as the square root of x to the 5th. Remember there's an understood 2 there? Because then you can think of it as this is x times x times x times x times x. So for these 2, 1 comes out. For these 2, 1 comes out. Trying to find my little button, my head's in the way. Alright, so this was under the square root and the 4. So under the square root, you still have this one guy. So we have 4x squared square root x. I'm really okay with you leaving it like this. I'm betting that answers in the back of the book would look like that. If you're looking at a multiple choice option, like on the ACT, it's more than likely going to have this guy. Okay? All right, I believe that is all. It is. All right, so we're going to do 5 through 100 multiples of 5. That keeps you down to like 20 problems to practice. Again, remember the odds. The answers are in the back of the book, so you can check your answers. You're welcome to email me with questions. I'll be happy to record a video of me working a few more problems or a specific one you're having trouble with. Just let me know.